Welcome to qnawire.
Let's start out by drawing the force diagram whenever the force is directed down the ramp. And so if this is my object on the ramp, then I have a normal force going this way. I have gravity going down. I have the applied force going this way. I have a friction force opposing the motion. And I'm going to break up this gravity into forces along and perpendicular to the ramp. And so this is the angle that they give us. And so this component here is mg times sine of 55, which is the angle they give us. And then this is mg cosine of 55. And now we're ready to apply Newton's second law. This is my coordinate system, by the way. It's positive x goes down the ramp and positive y goes upwards from the ramp. So the sum of the forces in the y direction equals 0, since the acceleration in the y direction is 0. This implies that the normal force is equal to mg cosine of 55, since those two forces are the only forces in the y direction. Now, plugging in values here, I get that the normal force is 56.21 newtons. And then when I plug this in to find the friction force, I get that it's equal to the coefficient of kinetic friction, since the box is moving, times the normal force, which I should be consistent and indicate by a lower n as I did here. And then when I plug this in, I get 16.86 newtons. Now I'm going to apply Newton's second law in the x direction. In this case, there is an acceleration, so it's not equal to 0, it's equal to mass times acceleration. Plugging in all the forces in the x direction, I get positive F plus positive x component of weight, or of gravity, I should say, minus the friction force, because it's in the negative direction. And this is equal to mass times acceleration in the x. We're solving for the acceleration. We just found the friction force. The applied force is given, and the mass is given. So everything in this equation is given, and we're solving for the acceleration. And so when we plug all of that into the calculator, we get that the acceleration is positive 18.34 meters per second squared. So this is the acceleration down the ramp that the box experiences. In part B, the only thing that changes is now the applied force is upwards and the friction force is downwards, so they swap places. The normal force is still this way, gravity is still down, and it still has the components, the same exact components that I won't write out again. But they are there. Now, the friction force is still 16.86 newtons, because it's derived purely from the normal force and the coefficient of kinetic friction, and both those quantities did not change with this new situation here. So this is still the friction force. And now I'm just going to go straight to applying Newton's second law in the x direction. So there it is there. And now I just need to substitute in for my forces. I have a positive friction force now, a positive weight contribution or gravity contribution. So it's sine of 55. And then I subtract my applied force because it's now in the negative x direction. And this is equal to mass times acceleration in the x. Now, once again, like last time, everything here is known except for the acceleration, and that's what we're solving for. So when I do solve for it, I get the acceleration is equal to negative 2.286 meters per second squared. So the acceleration is up the ramp by this amount. And it's much less because gravity is working against us now. And that's the